Thank you very much. Also, I'd like to thank the organizers for letting me speak here, and also thank you all for coming to the talk. I know I think it's still early, but I'm from the States, so it's all early for me. Okay, so I want to talk to you all about Jónsson filters. So first thing I want to do is start with defining what a Jónsson cardinal is. So we're going to say that lambda is a Jónsson cardinal if anytime I try to color the finite subsets of lambda in lambda many colors, I can find a set of size lambda, subset of lambda of size lambda, such that if I look at the coloring restricted to the finite subsets of A, I miss at least one color. So here, this is sort of related to, this is just sort of a weak Ramsey-ish kind of demand here, instead of asking that everything sits in one cell. So here we're saying that this A is weakly homogeneous. There's a definition in terms of algebras, but I never find that useful. So for those who might know, like lacking Jónsson algebras, that's the same idea. There's an equivalent definition in terms of elementary submodels, though, which, in addition to the coloring version, is actually quite useful as well. And the argument just involves Skolem functions. But basically, the idea is that lambda is Jónsson if and only if I can fix for any regular chi, and we can demand a parameter in h chi. We can find some elementary submodel that's sort of weird. That is, its intersection with lambda is size lambda, m sees x and lambda, but m has some gaps with respect to lambda. So I'm going to be talking about these models a lot. So instead of just saying a model that satisfies all these conditions, I'm going to use some shorthand and just call them Jónsson models. Sometimes I might say an x Jónsson model if I need to refer to a particular parameter x. Okay. So just to kind of give you an idea of what Jónsson cardinals, what we know, what some properties thereof, right? So Jónssonness sits between measurability and zero sharp exists in terms of consistency strength. So it's sort of in that weird gap area where most cardinals defined by partition relations exist. There's also a nice little result that if lambda is a regular Jónsson cardinal, then every stationary subset of lambda reflects. So this immediately tells us that, for example, successors of regular cardinals cannot be Jónsson. On the other hand, what's interesting about Jónsson cardinals more is what we don't actually know. So, for example, we don't know, this is a problem that probably most of you are at least somewhat familiar with in passing, but we don't know whether or not it's consistent as a singular cardinal mu such that mu plus is Jónsson. Even more hilarious I think, is that if lambda is inaccessible, I can ask sort of what large cardinal properties lambda inherits, like inaccessible Jónsson, I can ask what large cardinal properties inherits from below, right? So for example, measurable cardinals are Malo in a very strong sense, etc., and Ramsey in a very strong sense. Whereas with Jónsson cardinals, we actually don't know a whole lot. In fact, we don't know, for example, lambda is lambda plus Malo, and the best result along these lines is due to Schiller. Maybe a different one. Sorry. So if lambda is inaccessible Jónsson, then lambda is lambda cross omega Malo. And for those of you who sort of have forgotten Malo degrees and how they work, which is totally understandable because I rarely see this nowadays, we'll kind of discuss what that is in a minute here. But this is sort of a very large gap between there's a very large gap. And then there's this one I added just for fun. Is it consistent that alpha omega is Jónsson? I have no idea about this problem. I know a lot more about the first two. So here we're going to focus on basically the phenomena of regular Jónsson cardinals, and sort of at least attempting to, and the idea here is that we're going to find things called Jónsson filters, and maybe they'll be able to help us fill in the picture a little bit better. So let's go to a Jónsson filter, right? So we're going to say a filter is Jónsson. So lambda is a Jónsson cardinal. We're going to say a filter on F is filter on lambda is Jónsson if F is uniform, and there's a coloring which witness sort of the almost failure of Jónsson. That is, the range isn't, so anytime I fix an lambda size subset of lambda, the range is actually contained in F. So it sort of fails to be, witnesses a mod F failure of Jónsson. Just to sort of have some notation here, IA is a Jónsson ideal if its dual filter is Jónsson. I have a tendency of working with ideals on occasion, so just so I can flip back and forth between the two. It does have an equivalent definition in terms of elementary submodels as well. So if it's Jónsson, if it's uniform and there's a regular chi greater than lambda, x in h chi, such that anytime I have a Jónsson model that sees x, f swallows m's intersection with lambda. Uniformity, the sort of uniformity assumption here, that right, if I have a uniform Jónsson filter, then I have two Jónsson models, M1 and M2, right? Its intersection with lambda then has size lambda, so M1 intersect M2 is also itself a Jónsson model. So I can use this to build sort of descending chains of Jónsson models of a certain degree. And that's generally where that's actually going to be used here. So, of course, we might want to ask ourselves, why do we want to look at Jónsson filters, right? We can isolate a notion, we can define a definition, but it doesn't really matter unless we have some meaning, some sort of reason behind it, right? So it turns out that Jónsson filters appear somewhat in disguise in a lot of the work regarding solving problems about regular Jónsson filters, or regular Jónsson cardinals. So here we have this sort of theorem of Shala that says that if mu is singular, so that mu plus is Jónsson, then there's a Jónsson filter on mu plus. And in fact, this filter is dual to a sort of nice club guessing ideal. And they rise actually rather naturally. And the condition, so that's kind of where the notion of using that coloring kind of came from. I do want to note here that that coloring is sort of almost the opposite, that capturing the range of a coloring, sort of the opposite of Ramsey ultrafilterness, right? It's on the other end. So another thing is that they do get used in the context of inaccessible Jónsson cardinals, except, well, this is a bit of a, they're not really explicitly stated here, but they're not used explicitly here, but they kind of appear in the background and sort of in disguise when working with inaccessible Jónsson cardinals. All these proofs, all these results are from Shala, but basically the idea is that you assume that lambda has some small Malo degree and use this to build looks almost like a club guessing ideal in most cases. And then what you do then is you use this, actually use this Jónsson ideal to show that lambda has to have large Malo degrees. So this Jónsson filter, I guess, I say Jónsson ideal, yeah. This Jónsson ideal sort of acts as a middleman between these, sort of getting this contradiction here. So what I want to do now is I'm actually going to focus on this case where lambda is inaccessible, because part of the reason I want to do this is because a lot of work in this problem is not very well known, and also it's hidden in some, not hidden, but some of the work is hidden in sort of rather impenetrable papers of Shala, so I wanted to take some time to highlight some of these things. Okay, right, so the idea, so kind of to advertise, right, why we want to use Jónsson filters, I want to actually, my original plan was to do some PCF theory, but that would, my talk is 20 minutes, so about 15 of that would be spent being like, here's PCF theory, and then result, which is not perhaps illuminating. So instead what I want to do is I want to exhibit, sort of sketch an easy proof of this result, right? So this is from the book, and by the book, and I guess I mean cardinal arithmetic. So if lambda is an accessible Jónsson, then lambda must be at least lambda Malo. This is a weaker result than this, but there's a reason I want to look at this result in particular, because it serves as almost a test case. So instead we could ask about colorings of pairs. So instead of asking that lambda is Jónsson, we can ask that lambda satisfies partition relation, this square bracket partition relation. Right, so instead of asking for colorings of finite sets, we're asking for colorings of pairs here. Right, and then we know this is also due to Shala. I guess I'll just leave this here. Oh, and inaccessible. If lambda is inaccessible, lambda satisfies the square bracket partition relation, then lambda is omega Malo. That is an extremely wide gap between what we know about colorings of pairs and what we know about sort of colorings of finite sets. And the idea here is that we can equally define Jónsson filters sort of for colorings of pairs by asking then that the filter swallows, there's a coloring of pairs that such that the filter, and a filter such that the filter swallows the range of these pairs, these colorings. And the idea is this is sort of a test case for trying to bump this result up to saying that lambda is lambda Malo. That's at least the idea. So here, this is sort of the motivation I have for working through this result. Okay, and also it gives us an easy proof of a result that is a little bit impenetrable. Okay, so we need some definitions. I apologize. This is actually not nearly as, I realized I shouldn't have said here's the whole block. But the idea is pretty simple, right? We're just gonna, if I have a stationary subset of delta, I'm gonna measure how stationary it is, right? The depth of the stationarity. So its rank is 0 if S is non-stationary in delta. It's greater than or equal to 1 if it's stationary in delta. Its rank is greater than I plus 1 if and only if the set of ordinals where basically S reflects at rank I. And then if I is a limit, then rank is greater than or equal to I, if and only if it's greater than or equal to j for every j less than I. For those of you familiar with the malo operator, this can all be coded in terms of maloness and trace, except we're sort of off by 1 until we hit the omega malo stage. But it's a pretty similar idea, and you can extend this to, right, we're going to get sets of rank lambda only here, but we can extend this to rank lambda plus using canonical functions, but I didn't want to define canonical functions, so we're only going to stop for the result I want to talk about here. So lambda, we would say lambda is gamma malo if we let S be the set of inaccessibles, then the lambda rank of S is gamma, right? So we're just asking, maloness is related to how often the set of inaccessibles reflects.
So non-reflecting stationary is rank 1?
Yes, that's correct, yeah, thank you. Okay. So another thing we're going to need here is this map gets used pretty often in a lot of Shalaw's work, but it doesn't really get isolated. So here we're going to say that if M is lambda is Jónsson, M is a witnessing Jónsson model, we're going to find a map from lambda to M intersect lambda by looking at the sort of copy, I guess sort of the first point M at or above alpha. So if alpha is in M, then this ordinal is just alpha. If it's not, then beta M alpha is a limit ordinal of uncountable cofinality just by using minimality and elementarity. So you have this sort of gap here, right? M might see, so let's say that alpha is equal to sup M intersect alpha, so it goes up to here, almost hits alpha, then there's this large gap in M, and that's what we're going to try to exploit here. The wonderful part about these ordinals beta M is that they have this sort of, I sort of call this club indiscernibility, that might not be the best term, but basically M has a hard time telling the difference between, whenever I have clubs, M can't really tell the difference between alpha and beta M alpha, even when alpha is not inside M. So if M is a Jónsson model, if I have, if alpha sits in, if I have a closed set of ordinals, a sufficiently closed set of ordinals, and alpha is inside E, then beta M alpha is also inside E. Another thing, this is the part that gets used in that Treba-Wooden result that I mentioned earlier, is that if I have all these conditions, right, delta is equal to sup M intersect delta, delta is not in beta M, and D is a club of beta M that sits inside M, then actually delta is in the accumulation points of D. So this sort of club indiscernibility phenomena, gets used quite often when we're talking about maloness, because maloness is witnessed, or sort of stationary rank is witnessed by clubs, basically. Okay, so I want to explain why a little bit. So here's the first part, right? Suppose that lambda is an inaccessible Jónsson. If the model degree of lambda is equal to gamma, which is small, then for every regular cardinal theta between lambda and gamma, there's a theta complete Jónsson filter. Now, originally when I prepared this, I said, I will write the whole proof, I'll give a nice sketch of this argument. And it got a little out of hand, and I pared down the sketch until it was reasonable. And unfortunately, making it reasonable sort of boiled it down to kind of a lie. This is real. So basically the idea is, this is a very, very, very rough sketch, right? So the idea is we build a nice club guessing sequence, and this uses the fact that lambda has small malo degree. This is, so 1 and 2 are hard, 1 and 3 are hard, 2 is obviously very easy, right? We just fix a sequence, done, that's hard. And then what happens is we essentially use the club guessing to show that each M eta in this sequence swallows, there's a large set of delta where each of these M eta swallow the same non-small portion of C delta. And that has to do with the fact that Jónsson models tend to swallow non-accumulation points of clubs in club guessing sequences. So if I guess an appropriate type of club, what happens is that I see this sort of same portion over and over again, and then I look at the intersection, each of these M etas, the intersection contains all these non-trivial portions of a large set, so that intersection has size lambda, and so that tells me that the filter generated by M intersect lambda for M an appropriate Jónsson model actually ends up being a theta complete filter. That is a very, very rough sketch. The proof of this result essentially glues together some techniques of Shalaw. So it's this part here that kind of is hidden in the background that gets exposed in the proof. that allows us to give a very simple proof of the rest of this proposition. So we believe this, right? Then we also have this one. Suppose that lambda is inaccessible if there's a theta complete Jónsson filter on lambda. Oh, thank you. Then its rank is large. Okay, so if we think of this, right, theta complete Jónsson filter, and if I model the stationary set of, I have the stationary set of inaccessibles, so if I'm gamma malo and I have a theta complete filter, then the stationary set of inaccessibles should reflect theta often, and that gives me my contradiction. So, okay. I want to point out here that I did include the sketch of this result because it's sort of easier and it gives us an idea of how to use Jónsson filters, but this essentially follows from a result of Shehzad using Jónsson games. So I don't want to take credit for this one, but the proof is pretty nice, I think. So I'm going to try to sketch the argument in the remaining-ish time I have. All right, so here I'm going to fix, so I have a X Jónsson filter F, and so what I'm going to do is fix a stationary lambda, and I want to show that the lambda rank of S is greater than or equal to gamma. If I can show this for all gamma less than theta, I'm done, right? Okay, so the nice part here is that this rank, the stationary rank of S is witnessed by these, by clubs. So basically what I'm going to do is I'm going to fix club subsets of delta, and then I'm just going to ask that if cofinality delta is large, have that rank alpha of S intersect alpha is less than rank delta of S intersect delta. So basically this should happen on a club, and then if alpha is of cofinality omega or whatever, then we just, or it's non-stationary, S intersect delta is non-stationary, then we just demand that S intersect alpha is non-stationary. Okay, and I kind of already mentioned this, right? These clubs serve as witnesses that this thing has small rank, right? So this is where we use our Jónsson filter here. There we go. Here's the sort of obligatory technical jargon here. But the idea is pretty simple, right? We just build a tower of Jónsson models. Each of these, so N0 is just elementary and H chi. It sees this, oh, this H shouldn't be here, I'm sorry. I didn't define H, and my bad. Anyway, it's not important. So anyway, this, it sees that club sequence witnessing the rank of S, and then each successive stage, I just sort of look at N psi. I just wanted to see the previous N etas. And I asked that gamma plus 1 is contained in N psi. The idea here is that I want each N psi to be able to see the N etas. I can always demand this. So anyway, now I use this Jónsson assumption, and I define this sort of descending chain of Jónsson models by taking intersection, right? And I use the theta completeness here. So to use notation a little bit, right? Beta m psi delta, which is the the least ordinal in m psi above delta, or at or above delta. That's just going to be beta psi delta. Okay, so cool thing happens here is that by sort of leveraging some of these assumptions, we can actually build a strictly increasing sequence of ordinals. So these beta xi's, or beta psi delta, are a strictly increasing sequence of ordinals above delta. So if we do get this, it's not actually too hard. It's just sort of gets into the weeds a little bit. So if we do this, right, then we get that delta is an E beta for each psi, and right, that just falls from that club indiscernibility thing again, because E beta psi is always inside each of these models, and also that if epsilon is less than psi, then beta epsilon is in E beta psi. Okay. Once we have these assumptions, right, we can argue inductively that the beta psi rank of S intersect beta psi is greater than or equal to psi for each psi, right? Because we have this assumption earlier, that rank delta of S intersect delta is less than rank lambda of S, this tells us then by induction of S must be greater than or equal to gamma. So at stage 1, it's pretty simple. All we're going to be doing here is we're just going to ask that, right, if delta sits inside S intersect E beta 1, right, we get the usual tree. This is actually the usual tree Wooden argument, right? It gives us every club that's inside here. It's club of beta 1. It should be beta delta 1. I'm sorry, I dropped a delta here. That's inside N prime M1. My notation got a little bit screwed up. I apologize. This should be an M1 here. So anyway, it sees delta as an accumulation point. So by elementarity, S intersect beta 1 is stationary. Okay? And then finally, the last part is that, well, if psi is greater than 1, then by induction we know that rank beta psi of S intersect beta psi delta, these should be deltas, is greater than epsilon for each epsilon less than psi. So as epsilon sits inside E beta psi, it follows that E beta psi must have, so because epsilon sort of serves as a witness, beta epsilon sits inside here, so rank beta psi, S intersect beta psi is greater than epsilon. So here we can see this essentially. The point of this is that this is a beefed up or sort of strengthened version of the Treba-Wooden argument that gets you that every stationary subset of lambda reflects under the assumption that lambda is Jónsson. So we just use this Jónsson filterness property to actually sort of beef this up and strengthen it a little bit. And I think that's actually going to be it for me. So thank you.